Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we're continuing in the last lecture. In the last lecture, we discuss the idea of, let me write it clearly. We discuss in the last lecture the idea of phase space. Where is this? Okay. So in the last lecture, we discussed the idea of phase space and ensemble, or we call it ensemble. We said that the state of a system in classical mechanics with F degrees of freedom, Q1, Q2, Q3, up to QF, these are generalized coordinates, and the corresponding momenta P1, P2, P3, up to PF. So if there is this state in classical mechanics in the system specified by F degrees of freedom, we specify the state by constructing a 2F dimensional space dimensional space, one dimension corresponding to each coordinate and momenta, called phase space. Now in this phase space, each point will specify the state of the system, and if we know the point in phase space, there is a location of the point in phase space, from that we can completely predict the future behavior of the system. That means we can predict all the future states of the system, and also we can make prediction about all the previous states through which system has gone to reach that particular state. Then we talked about the idea of the cell. We said that we can divide this phase space into cells in 2 dimensions. When we talk of a particle moving in 1 dimension, in that case, our phase space is just 2-dimensional, one corresponding to, in generalized coordinates, Q and another P. Then we said we can divide this space into small cells, and the area of the cell, delta Q, delta P, is equal to some constant h naught with units of angular momentum. Then we said that this h naught can be arbitrarily small, can be arbitrarily small in classical mechanics, because it is possible in classical mechanics to specify the position and momentum of a particle to an arbitrary accuracy simultaneously. So this h naught can be as small as possible. But in quantum mechanics, there is restriction on this specification, and that restriction is specified by the Heisenberg's uncertainty principle, which says that it is not possible to specify the position and momentum of a particle simultaneously to an arbitrary accuracy. Therefore, according to this principle, you know that delta Q, delta P is greater than or equal to h bar by 2, where h bar is h by 2 pi and h is Planck's constant, and you know its value. H is 6.6 into 10 raised to power minus 34 joule second. So this places the restriction on the specification, simultaneous specification of the position and momentum of a particle. So when we place this restriction, this H naught as the size of the cell cannot be arbitrarily small. It can be at least H cross by 2 or H by 4 pi, right? So this is the difference between the classical phase space and quantum phase space. So you need to take this into consideration. Now, in general, for f degrees of freedom, how we write the volume of the cell, write it this way. In general, volume of the cell in phase space is written as the product of delta Q1, delta, let me write it clearly, delta Q1, delta Q2, delta Q3, then you the product of the corresponding moment extensions, delta P1, delta P2, up to delta PF. So this is in general the volume of the cell in f dimension, 2f dimensional phase space when we have a system of f degrees of freedom. And if the delta Q, delta P, K, delta Q, K, delta P, K is taken equal to H naught, that means if the area of the cell corresponding to kth coordinate is taken at H naught, then this will become H naught. This will become H naught raised power F, where F is the number of degrees of freedom, right? In fact, this expression for the area of this cell in the phase space reduces to this equation when you consider the one-dimensional situation, right? Or 1 degree of freedom situation. Now you need to understand that how the system moves in future, that means the motion of any phase point is an unambiguous function of its instantaneous position. We have discussed this already, that if we know the position of phase point in the phase space at a given time, we can predict the motion of the system in the phase space in all future times and all past times, right? Then we discuss the idea of ensemble. I will elaborate on that first. We said that if we have some system of interest that we discuss this way, first we will connect it to the previous lecture. If we have some system in question, in the last lecture I told you, if we have a system consisting of 3 dice, now you want to throw this glass of 3 dice, you will have many outcomes. By outcome I mean which is the uppermost side of the given dice. You know, for each dice there are 6 outcomes, and because it has 6 edges, and on each edge there is uh, written the number of dots. One has dot 1, then we have 2 dots, 3 dots, 4 dots, 5 dots, and 6 dots. So if you throw a single dice, then you have 6 outcomes. Now in case of this 3 dice situation, you will have total number of outcomes as uh, 6 raised power 3. You will have 6, write it clearly, you will have 6 raised power 6 raised power, pen is not working properly, 6 raised power 3 outcomes when you take this 3 dice situation. If this is my system of interest and I want to make prediction of I want to make prediction of its average behavior. So what we do, we conceptualize a collection of identical systems. Collection of identical systems means you construct many copies of the system, all must be identical. That means the dice 3 must be similar, identical in all respects, place it in this glass identically. So this then, to find the average properties or average behavior of this system of interest, you average over all the systems in this collection. You conceptualize a collection of identical systems and focus attention on their outcomes separately. Then average over all the outcomes in this collection of identical systems, and that average behavior is corresponds to the average behavior of the system of interest. Now such a collection, I will change the color of my pen, I will use red. Now such a collection of systems is called ensemble of systems, right? I will give you another example. Now, when we talk of this ensemble of systems, are such situations where we have a system of interest, we want to find its average behavior, and we construct ensemble of the systems and average over those systems to get the average behavior of the system in question. We talk of macrostate and macrostate. We talk of the idea of macrostate and microstate. So let me make this clear first. You know it from the study of your thermodynamics. I will refresh your memory. So if I have a container, so I have some container containing 32 grams of oxygen gas. You know this container containing 32 grams of oxygen, this is my system of interest. That means I want to make prediction about its behavior. So this container will contain Avogadro's number of oxygen molecules, because 32 gram is the gram molecular mass of oxygen. So it will contain Avogadro's number of oxygen molecules, that is 6.023 into 10 raised power 23 molecules. Is a big number. So if you want to give the description of the system in microscopic terms, that's called using the microscopic method. So what is the microscopic method? Microscopic method means you use the laws of mechanics to find the trajectories of all the particles. So for that, what you have to do, since these molecules were assuming that they are moving freely, so for each molecule, you have to specify 3 positions because it is moving in space, and 3 velocities, Vx, Vy, and Vz. That means for each particle, you have to find out the dependence of these 6 coordinates. You have to find x of t, which gives you dependence of its position on time. You have to find y of t, which gives the dependence of its y position on time. And you have to find z of t, which gives dependence of its z coordinate with time. You have to find Vx of t, which gives the dependence of velocity along axis on time. Then you have to find Vy of t and Vz of t. For that, what you do, you construct using Newton's laws, you construct the differential equation. knowing all the forces, then you use Newton's second law, then you solve that differential equation, and once you solve that differential equation, you put the initial conditions of initial position and initial velocities, then find out the future position and future velocities. Now, if you do this way, describe the system, you have this much number of particles. When we are talking of 1 mole, then corresponding to each molecule, you have these 6 coordinates, 3 velocity, 3 position coordinates. So for this much number of particles, you will have to specify 6Na, which is 6 into 6.023 into 10 raised power 23 velocity coordinates and position coordinates in total. So for this system, you will have this much number of equations, 6Na number of equations to figure out. This is microscopic description of the system. For each particle, you have to find its trajectory, means you have to specify these 6 equations, and then for any number of molecules, you have to construct this much number or figure out this much number of equations. Then you can predict the system with classical mechanics. When you do this detailed description of the system, we call it microscopic method. We call it microscopic method. The question is this possible? See, the number of equations is so much huge that if you just list this number of equations at the speed of writing one equation using at 1 second, that means if it takes you to write one equation 1 second, then this much number of seconds will be just required to list the equations. It is huge. This becomes, if you calculate, billions of years. So reason is the number of variable is large. So this is too much information to handle. So I will say that it is indigestible information. It is too much information to handle. So this class, and remember, we are ignoring the vibrations of the molecules, and we are ignoring their rotations. If there are rotations, there are vibrations, the number of variables will further increase. And if you increase the number of molecules, you make it 2 mole, 3 mole, then this is further going to be further complicated situation, because the number of variables will become large. So we say the information is indigestible. So microscopic method is not possible. Not possible, right? Then what we do, we talk of macroscopic method. So let me discuss now the macroscopic method. Now, in macroscopic method, what we do, we ignore the internal details of the system. That means we take certain macroscopic properties of the system. For example, we consider the pressure in the gas, we talk of temperature of the gas, we talk of volume, V, volume occupied by the gas, volume occupied by the gas. We talk of internal energy. We talk of internal energy. We talk of heat put into the system, work done by the system. So this is a small number of variables which we have to handle. Then what we do using these, we call them macroscopic variables, we specify the state. So when we specify the state of this system using these macroscopic variables, their number is small, so advantage is huge. But what is the cost of doing this? We are disregarding the internal details of the system. We are disregarding where these molecules at a particular time are located and with what speeds they are moving. So we are ignoring those details. We take the overall behavior of the system into consideration. Now, this state specified by these macroscopic variables is macroscopic state. And the state specified by the microscopic variables, that means all the positions and velocities of all the molecules at a particular time, is microscopic state, right? Now, for a given macroscopic state, there are many microscopic states possible. That means if I have a gas in certain macroscopic state, for example, which is specified by some value of pressure, some value of volume, some value of temperature. Now the system is in equilibrium. That means it is in settled situation. It has acquired some pressure, some volume, some temperature. But internally in the system, the molecules are moving. Their positions, velocities are changing. That means microstates are changing, but the macrostate is specified. So corresponding to a macrostate, given macrostate, there are many microscopic states. So I hope it is clear now to you. So if I have a system where a huge number of variables are there, microscopically, the information is indigestible. So the microscopic method is not possible. We talk of in terms of macroscopic variables. They are few to handle, but cost is that we are disregarding the overall internal details of the system. So corresponding to each macrostate, there are many microstates possible. Now same is the situation here. Now compare the situation. Now, we have this system of interest, this gas. We want to make, this is now our system of interest. If we have to predict the average behavior of this system, what we do, we construct an ensemble of systems which are identical, then we average over those systems in the ensemble to find the average behavior of the system of interest. So it is not just the situation of that dice. This ensemble's idea is used whenever we have a system of interest and its behavior is difficult to predict when we talk in terms of all the details of the system, that is microscopically. Then we use the idea of macroscopic state and we construct an ensemble of systems, then predict its average behavior using the average over the ensemble. So I hope it is clear. So same is situation for this gas. Now I will give you the example, simple example of the macrostate and microstate. Suppose I have four distinguishable particles. I have four distinguishable distinct this is not correct spelling, distinguishable particles. Distinguishable particles mean I can make distinction between them, I can label them. So I have four distinguishable particles. Now I name one or label one as particle 1, second as particle 2, third as particle 3, and fourth as particle 4. Now I specify my macrostate this way. So I specify by macrostate that there be two states possible. By two states, I mean, suppose I have some container with two chambers. A chamber 1 I call state 1 and chamber 2 I call state 2. Now I tell you my macrostate is two particles in each state. Two particles in each state. So this is my macrostate, right? I'm giving you two state system. That means I'm telling you I have a container with two chambers. So I am placing the restriction. You have to place two particles in each state. That means two particles in each chamber. But I am not putting restriction on which particle is to be placed where. That is not the idea of macrostate. Now there are, if I ask you what is the number of microstates, what is the number of possible microstates corresponding to this macrostate? Which macrostate? Four distinguishable particles. You have to place two particles in each state. Now, what is the number of possible microstates corresponding to this macrostate I'm asking you and list all the microstates. If you think about it, it is simple. You have to just distribute the particles, two particles in each state. One possibility is that I place particle 1 and 2 in state 1, 3 and 4 in state 2, that is chamber 2. This is my one microstate. What is the second possibility? Second possibility is I place 1 and 3 in state 1 and 2 and 4 in state 2. What is the next possibility? Next possibility is I place 2 and 3 in state 1 and 1 and 4 in state 2. What is the next possibility? Next possibility is you place 3 and 4 in state 1 and 1 and 2 in state 2. Next possibility is you place 1 and 4 in state 1 and 3 and 2 in state 2. There is one more possibility. You place 2 and 4 in state 1 and 3 and 1 in state 2. If you check, there is no repetition. In first, we have 1 and 2 in state 1, 3 and 4 in state 2. In second, 1 and 3 in state 1, 2 and 4 in state 2. In third, 2 and 3 in state 1, 1 and 4 in state 2. Then you have 3 and 4 in state 1, 1 and 2 in state 2, then 1 and 4 in state 1, and 3 and 2 in state 2, then 2 and 4 in state 1, and 3 and 1 in state 2. There is no other possibility. If you check it at your home, only these 6 microstates are possible, right? So this is how we construct microstates corresponding to a given macrostate. But this idea is general, as I told you. We talk it whenever we have. Here it was easy to figure out the number of microstates possible, but it is not always easy when the number of particles is huge and number of states is large. This way you cannot list them, but you can. That will be very inconvenient because the states will be large. But the basic idea is this, which you have to understand, that whenever we have a system to deal with where the number of variables is large to make prediction about the system, then what we do, that means when we have that microscopic method to deal with, but the number of variables is large, then we talk in macroscopic details, macroscopic variables, we ignore internal details, then we make prediction about the average behavior of that system of interest by constructing the ensemble of systems, which are a collection of identical systems, right? Now, let me move to again the phase space. In the phase space, let me go to the first page. In the phase space, we said that each point specifies the state of the system at a particular time. Now, if I have some ensemble of systems and I have to depict their state in the phase space, In the phase space, each system in the ensemble which we are considering which will have a representative point in the phase space. But when we consider the ensemble of systems as a whole, pertaining to that, there will be a cloud of points, right? Corresponding to each system in the ensemble, there will be a point, and corresponding to ensemble of systems, there will be a cloud of points. That means the group of points which will specify the condition of the ensemble at a particular time, right? As time proceeds, all systems will evolve that in the ensemble. That means all points will move. So this cloud will move in the phase space, which represents the ensemble, right? So I hope it is clear. I am stopping here. Next time we will discuss more ideas. Thank you. Assalamu alaikum.